going to talk a little bit about the Belmont Bridge replacement project, Whitman County. We built this last year. The Belmont Bridge was a replacement project for a 1921 all-wood structure. It was 19 feet long and 22 feet wide. The original wood structure was built in 2000, or was rebuilt, in 2002 on original wood piles with wood back walls. The bridge was experiencing lots of deterioration and lots of flooding going on. This bridge had actually been overtopped a couple of times since I've been at the county. The replacement bridge, as with many in Whitman County, was planned. I'm sorry, I didn't even advance the slides. Was planned to have a longer span in order to improve the hydraulic opening of the bridge. This also makes it easier to build new foundations behind the existing wood pile foundations. The channel, Kelly Creek, has an average mean channel width of about 20 feet, and the road approach on both sides of the channel is normal to the channel alignment. Therefore, neither the existing bridge nor the replacement required any skew. That made it fairly simple. One of the goals of the replacement bridge was to open up the channel wider than it was and raise the bottom chord of the bridge to get it above the 100-year floodplain. Whitman County has a dedicated bridge crew of 5 people and has the equipment and experience to replace small bridges with county forces. We've been doing this for many years. Until recently, the county has traditionally constructed concrete superstructure bridges and then only recently switched over to steel superstructures for much of what we do. The county builds the foundations and all the site work and contracts for the casting and the delivery of the pre-stressed concrete, or in this case, the manufacture of the steel girder superstructure. For the Belmont Bridge, we competitively bid the manufacture of both the steel and the concrete. The successful bidder and the lowest cost was True North Steel with a steel rolled beam steel structure. True North Steel is out of Missoula, Montana. Another nice thing to note is that when we bid these out, we asked for the manufacturer to actually produce the shop drawings and stamp them. So here's a couple of pictures of us taking down the old bridge. Basically, when we moved the old structure, the county forces tries to isolate the area of the construction and make sure that we're not dropping a lot in the creek. It's impossible to do that perfectly, but there's a lot of real requirements on that by Washington Fish and Wildlife. So we do our best to isolate the site. So Whitman County has been building bridges using county forces for several decades. County forces are capable of building bridges up to about 60 feet in length. This is a practical limitation just because of the time available. The same people that build bridges also maintain our bridges. We have over 300 bridges to maintain, so that it's a big time commitment. Typical earth materials consist of soft, firm silt and clay alluvial soils overlying basalt bedrock. The alluvium is not typically suitable for support of the structures, particularly when considering scour potential. Therefore, most of our bridges we support using H-piles driven into the basalt bedrock underneath. The depth of the basalt is usually between 5 and about 30 feet, although we've had a couple of them show up at about 70 feet, which surprises us a bit. We found that it's a lot cheaper and simpler to just simply drive steel piles to bedrock and then build tieback anchors as mitigation if the final bearing depth is not below the scour areas. About 10 years ago, the county upgraded to a hydraulic pile driver that is mounted to a large track hoe to install the piles. You see the picture of it sitting right there doing this Belmont Bridge. The number of piles is determined based on the anticipated loading and the length of the bridge. Sorry, I have to use my paper because my screen is doing weird things. For the abutment pile cap, rather than forming and casting concrete and waiting for it to cure, the county installs a top plate or a pile cap using the same size H pile that we use to drive the piles. You see pictures of it there. Then we use steel back wall installed behind that to put the backfill up against, and then we compact structural fill behind that. This is a picture of basically the final product just prior to putting the bridge on it. By making the bridge longer than it once was, or in the old bridge, in fact, I'll go back just a little bit, and you'll see right there we're driving piles behind, right behind where the old abutment was. It makes it very simple for both safety on the job site and for construction. This simplifies all the requirements from Washington Fish and Wildlife as well. So it's really simple when we can isolate ourselves as much of the stream as possible. After the piles and the pile cap are completed, the old foundations can then be removed with less disturbance to the channel, and then riprap is installed. So the final dimension of the superstructure on this project was 32 feet long by 28 feet wide. So the bottom of the new bridge needed to be raised above the creek further than the original wood bridge. So the road was raised about 2 feet to accommodate the new superstructure. The modular rolled beam steel bridge consisted of 3 modules that could be shipped to the site on 1 truck rather than 3 trucks as we used to do with the old concrete bridges. Selecting a bridge structure that can easily be handled by 1 or 2 excavators significantly reduces the overall project costs and shortens the construction times. You can see here we're able to use a large loader in the trackhoe to basically put these modules into place. They're lightweight enough to do that with county forces and county equipment. Each module had 2 or 3 weathering steel rolled beam girders fully assembled and a corrugated steel deck and side dams attached. Now this is easy for placement of gravel riding surface. You'll note in the picture on the right, you'll see a steel beam or a steel rod right on top of the corrugated deck, and that's basically grader rails for when we put gravel over it later on. There's a couple of pictures, and there's a great picture in here. If you look in the upper right, there's Dr. Barker actually working on our crew. We decided not to rehire him this year though, but just to prove that he does know how to use a pry bar. So here's some pictures of the 2 girder superstructure modules being erected. The modules are shipped to the site and assembled with the side dams, simple cross frame diaphragms, and the guardrail stubs, as you can see on that left photo. There's no concrete curing time, so we can put the bridge into service rather quickly after this. So here's just a couple of nice pictures of the bridge sitting on top of the foundations. You can already see the restraining anchors put in place on the left, and then on the right you can see the fully installed modular pieces before we put any gravel or do any backfill to it. We did have to fix that sort of right corner that you can see in there. We had to put some gabions in there to retain the soil. Here's the next picture, adding the fill to the bridge. This was on a gravel road, and so you can see the gravel goes right across the deck. And this is prior to installing the guardrail on there. And you can see the soil spilling off to the right. So it gives you a sense for how easy that was to put together once we had all the pieces in. In addition to the direct cost, there's always indirect costs associated with the bridges. With their different superstructures. With a concrete superstructure option, Whitman County would have to hire a crane service to lift the concrete girders into place. With the steel modules, we did not need to hire crane service. Crane service in our area usually runs $4,000 to $8,000 per spot, and that's assuming good access. The steel girders can be lifted with the county forces, just getting rid of all of that. And it also helps quite a bit with scheduling, because I don't know how many of you work with crane services, but scheduling them can sometimes be a 1 or 2 week option just to get them into the right spots. So this Belmont Bridge, the total cost of this project was about $168,000, and the concrete superstructure alternative was $85,000. If you look at the cost estimate right, or the cost breakdown, these are just rounded numbers. The steel superstructure was about $50,000 delivered to the site. The concrete superstructure alternative would have been about $85,000. So that alone was about a $35,000 increase had we gone with concrete. So we used to build exclusively with concrete. We believed it was a better product for a lot of years, and I think we have taken a little bit of time and rethought that a little bit. We now believe steel might be the better option for what we're doing, although any given or specific location you're going to want to look at individually to see what's the most applicable. So the Belmont Bridge was completed during the summer in accordance with our permit from Washington Fish and Wildlife. It took about 4 weeks to complete and then was open to traffic. There was a little delay in there for some internal issues, but the 4-week period was the total time building the project. The work included the installation of a temporary detour bridge, which is a single-lane steel bridge that was purchased about 8 years ago and used on all our construction projects for small bridges. The stream site isolation, erosion control measures, pile installation, pile cap installation, welding of the seismic anchor clips, the placement and completion of the superstructure, and all of the associated road building activities were all within that 4-week period. I think I already talked a little bit about that. We did a competitive bid on the structures, the superstructures, and that was the difference of 35,000. By the way, that's my bridge crew. They're just regular guys that know how to build things. So for a couple of quick takeaways, the steel bridge superstructure costs are competitive with other bridge materials. We found that to be very much true in the last couple of years. They can easily be constructed with county forces without specialized skills. They're lighter weight, resulting in economies in required construction equipment and substructure costs. Steel modular bridges allow for ease of erection, faster erection times, and the modules fit together great due to the quality of the shop fabrication. For long-term maintenance in this bridge especially, with the steel deck grader rails allow for the gravel road surfacing to go clear across the bridge, which makes it far easier for us to maintain a gravel road like this. I don't know who else maintains gravel roads with bridges, but it's the maintenance crew always has a hard time when they come up against a concrete deck with a gravel approach. So anyway, that is my quick and dirty presentation.